When you hear the words planetary protection, what do you picture? Giant space lasers defending Earth from hostile alien invaders? Maybe Will Smith punching an alien in the face? Well, the reality is a little less Hollywood and a lot more sterile. Welcome to G Fun Facts Online, where today we're talking about the real guardians of the galaxy, the scientists and engineers whose job is to prevent us from becoming the aliens we're so desperately looking for. As humanity sends its robotic explorers to Mars, Jupiter, and beyond, we're driven by that profound question, are we alone? But tangled up in that question is an equally profound responsibility. This is the science of planetary protection. It's not about fighting Klingons. It's about the meticulous, painstaking work of making sure we don't accidentally contaminate other worlds with life from Earth. And just as importantly, that we don't bring anything dangerous back home. It's the ultimate expression of the explorer's creed, leave no trace, but on a cosmic scale. At its heart, planetary protection is a simple but profound idea. It's a scientific discipline dedicated to two things. First, protecting other planets, moons, and asteroids from contamination by microbes from Earth. And second, protecting Earth from any potential life forms we might accidentally bring back. It's a two-way street, a cosmic quarantine. This whole idea is built on the fact that microbial life is incredibly tough. We find bacteria on Earth thriving in volcanic vents, frozen in Arctic ice, and in the most irradiated places on the planet. If they can survive that, a trip to Mars on the side of a rover doesn't seem so far-fetched. This brings us to the two fronts of this quiet war against contamination, forward and backward. Let's start with forward contamination. Think of it like being an incredibly responsible tourist. When you visit a pristine, isolated ecosystem on Earth, like the Galapagos Islands, you clean your boots so you don't introduce invasive seeds. In space, our spacecraft are the boots, and a world like Mars or Europa is the pristine ecosystem. The main reason we do this is for the science. We are spending billions of dollars and decades of effort to search for life elsewhere. Imagine the excitement of discovering microbial life on Mars, only to find out through DNA testing that it's a common bacterium from a lab in Florida that hitched a ride. That would be the biggest scientific facepalm in history. It would be a false positive that could permanently ruin our ability to know if Mars ever had its own native life. Then there's the other side of the coin, backward contamination. This is the one that sounds more like a sci-fi movie plot. It's all about missions that bring stuff back to Earth, what we call sample return missions. While the existence of life on other planets is still a big question mark, we have to act with caution. The chance of a Martian microbe, if one exists, being harmful to Earth's ecosystem is probably very, very low. But is it zero? No. And because the consequences could be so significant, we can't take that risk. It's the ultimate precautionary principle. Any mission bringing samples back from a place that could harbor life must be treated with extreme care. The returned material would be handled in highly secure, specialized biocontainment facilities, like the ones used to study the world's most dangerous viruses. You might think this is a new idea, a reaction to our growing capabilities in space, but you'd be wrong. The concept of planetary protection is almost as old as the space age itself. Scientists were already talking about it in the mid-1950s, before the first satellite even reached orbit. In 1958, the same year NASA was founded, the U.S. National Academy of Sciences recommended that spacecraft be sterilized. A year later, an international group called COSPAR, or the Committee on Space Research, was formed, and it became the global standard setter for these policies. This idea was so important that it was written into international law. The 1967 Outer Space Treaty, which is the foundation of all space law, has a specific section, Article 9. It basically says that all nations exploring space must do so in a way that avoids harmful contamination of other worlds and also avoids adverse changes to Earth's environment from bringing extraterrestrial material back. This treaty makes it every spacefaring nation's responsibility, whether the mission is governmental, like NASA, or a private company. Now here's where it gets really cool and detailed. Obviously, a mission to the Sun doesn't carry the same contamination risk as a rover drilling into the Martian soil. So planetary protection isn't one size fits all. Instead, missions are sorted into 5 categories, based on the destination and the type of mission. Category 1 is for missions to places that are not of interest in the search for life, like Mercury. For these, there are no special planetary protection requirements. It's a go-ahead. Category 2 is for missions to places that are interesting, for understanding how life's building blocks might form, but where the chances of life are still very low. Think of missions to Venus, or our own moon. These just need some paperwork to show we have a plan to avoid crashing and to document where the spacecraft ends up. Things get serious with Category 3. This is for flyby or orbiter missions to high-priority targets, like Mars, or Jupiter's moon Europa. Here, the spacecraft has to be cleaned to a certain standard, and there must be a very low probability that it will accidentally crash onto the surface. Category 4 is for landers and rovers that are actually touching down on these high-priority worlds. These missions have the most stringent rules to prevent forward contamination. They have to be assembled in special clean rooms and sterilized to reduce the number of microbial stowaways, what scientists call the bioburden, to an incredibly low number. For a Mars rover, we're talking fewer than 300,000 bacterial spores on the entire machine. Finally, we have Category 5. This is the highest level, reserved for missions that bring samples back to Earth. If we were bringing back rocks from a place deemed to have no chance of life, it would be an unrestricted return. But for a restricted return, like from Mars, it's the ultimate challenge. It includes all the intense cleaning of a Category 4 mission, plus the most extreme quarantine and containment procedures imaginable to protect Earth's biosphere from the unknown. So how do you actually clean a multi-billion-dollar robot designed to survive the vacuum of space? Very, very carefully. The process is an art and a science in itself. First, the spacecraft are born in captivity, built inside hyper-sterile clean rooms. These rooms have advanced air filtration systems, and technicians are covered head to toe in sterile bunny suits to minimize any contamination from skin or breath. Then, any component that can withstand it gets baked, literally. They are put in ovens at high temperatures for long periods to kill any and all microbes. This dry heat sterilization was used for the Viking landers sent to Mars in the 1970s, and it's still considered the gold standard of clean. For the more delicate parts, like sensitive electronics that would be destroyed by the heat, they use chemical sterilization. They might use gases like ethylene oxide or vaporized hydrogen peroxide, which can seep into every nook and cranny of the hardware and kill any surviving microbes. And throughout this entire assembly process, engineers are constantly taking swabs from the spacecraft's surfaces. They culture these swabs to count the number of viable spores, ensuring that the spacecraft meets its strict bioburden limit before it's cleared for launch. Why go through all this trouble? Because of a few very special places in our solar system that are our prime suspects in the search for life. Mars is obviously at the top of the list. We have overwhelming evidence that billions of years ago, Mars was a warmer, wetter world with a thicker atmosphere and liquid water on its surface. The key ingredients for life as we know it were there. While the surface today is a cold, irradiated desert, it's possible that life could have retreated underground, perhaps surviving in pockets of salty water. This is why we have special regions on Mars where we think terrestrial microbes could survive, and these areas are subject to the strictest protection. But Mars isn't the only game in town. Far out in the outer solar system, we have the ocean worlds. Jupiter's moon Europa and Saturn's moon Enceladus are both covered in a thick shell of ice, But beneath that ice, they are both believed to harbor vast, global oceans of liquid salt water. The combination of liquid water, chemical ingredients, and a potential energy source from the gravitational tug of their parent planets makes these oceans one of the most compelling places to look for life. Contaminating one of those pristine, hidden oceans would be a scientific tragedy of cosmic proportions. But as our technology advances, the field of planetary protection faces new challenges and controversies. The biggest game changer is the rise of commercial spaceflight. Companies are bringing incredible innovation to space, but it also complicates things. Under the Outer Space Treaty, the United States is responsible for the activities of American companies. This means regulators need to figure out how to ensure private missions meet these strict standards without crushing the industry. Then there's the ultimate contamination vector, us. Humans. We are walking, talking ecosystems, home to trillions of microbes. It is fundamentally impossible to sterilize an astronaut. This means that the first human mission to Mars will, without a doubt, introduce a significant amount of Earth life to the Martian environment. This has sparked a huge debate. Should we conduct a thorough robotic search for any native Martian life before we send people to avoid contaminating the evidence forever? Or is human exploration a necessary next step that we must find a way to manage? The current thinking is leaning towards a compromise, creating go-to zones for human missions that are of lower biological interest, while preserving other areas as no-go zones, protected for scientific study. So, in the end, planetary protection isn't about building shields against alien fleets. It's a quiet, meticulous promise we make to the cosmos. It's a demonstration of foresight and humility. It's the work that ensures that when we finally answer that age-old question, are we alone, we can actually be confident in the answer. It is the deep respect we show for the universe as we reach out our hands to understand it. Thanks for tuning in to G Fun Facts Online.